Logarithmic Properties, Part 3. There's a couple of properties, or a few more, not just a couple, that applies to, but a few more properties that are useful when we solve logarithmic equations or exponential equations, or do use these properties for other things. One of them is that basically you can take, if two things are equal, you can take the log with the same base on both sides of the equal sign, and vice versa. If you have log base b of m equal to log base b of n, that implies that the two things that are being taken the logarithm of will also have to be equal to each other. The proof for that starts the same way as the other ones. You let log base b of m equal x, log base b of n equal y, convert to exponential form, just like we did all the other proofs. The only thing is, this is a biconditional. It says if and only if. That means that if m is equal to n, then we can take the log of both sides. And vice versa is also true. If you're taking the log with the same base on both sides, that implies that the two things inside are going to be equal to each other. So we're going to prove it in both directions. Starting with the condition, or the hypothesis that m is equal to n. Then by substitution, I can substitute in, because I let these logarithms equal x and y. I know that m is then equal to b to the x and n is b to the y. So I'm just going to substitute in. Since they have the same base, it implies that the exponents must be the same. So therefore, I can conclude that x is equal to y. By substitution, again, I can substitute in from my given over here on the left-hand side in purple, that x is equal to log base b of m, so I'm substituting that in, and log base b of n is equal to y. So therefore, I've shown, if I start with m is equal to n, that I can conclude that the two logarithms are equal to each other. Same in this other direction. I'm going to start with, if the two logarithms are equal to each other, then by substitution, I can substitute in x and y for those two, based on what I have over here in purple as my given information. By reflexive property, I also know that b, as long as b is a real number, that b is equal to b, like a number is equal to itself in the real number set. And then I can raise both sides to the same power. If x is equal to y, then that implies that I can raise b to the x on one side and b to the y on the other side, because x and y are equal to each other. Then by substitution, I can then substitute in b to the x power is over here in purple, is given that is equal to m, and on the other side, b to the y power, it's given that that's equal to n. So therefore, we end up with m is equal to n. It's a long-winded way of saying, for example, if I had something like this over here on the side, let's say let's pick a color over here. I had log base 5 of x is equal to log base 5 of 7. Well, if that's the case, x would have to equal 7, like that. Or let's say I had like 2 is equal to 3 to the x. I could take the logarithm of both sides. Like, for example, the natural log of 2 and set equal to the natural log of 3x. And then in that case, move the x out in front. So we have log base 2 is equal to x times the natural log of 3, because of the power rule that we just proved. And then in that case, oh, look, I could, for example, divide both sides by the natural log of 3. So it gives us some tools where if I have something with an exponent, I could take the natural log or the log base 2 or whatever log base I want. I could take that of both sides, like that. Some other useful ones that are, you can think them out in a sense. You could say, all right, log base b of b, what should I raise b to get b is equal to 1? The natural log version of that, by the way, would be the natural log of e is equal to 1. If I wanted to prove it to myself, like the more formal way, like you don't have to do this every time, but just for now, I know that log base b of b is equal to 1. But for now, I'm going to let log base b of b equal to x. Convert that to exponential form. That means that the base is b, the power is x. that would be equal to, in here, this b here corresponds to what I'm highlighting in yellow. If that's the case, look, both sides of the equal sign have the same base. That means x would have to equal 1. Oh, I lost the x here. Whoops. I must have erased that by mistake here. Log base b of x is equal to, like that. That means x would have to equal 1. And then by substitution, if x is equal to 1, I can substitute that x in here, 1 in for x. So that means log base b of b is equal to 1. Or you could say to yourself, what do I need to raise b to get b? Well, that's just 1. I want you to try the other two. I'm just going to write the natural log version of that. If I have the natural log of 1, that is also equal to 0. For the next one, the natural log of e to the x is equal to x. And e to the natural log of x is also equal to x. It's the same proof, just with natural log. But these all mean the same thing. These are related to each other. So pause the video and try and prove these two to yourself. So here are the proofs. They follow basically the first one. Set the logarithm equal to x, convert. Look, that means x would have to equal this. Substitute for all of them. The last one is slightly different in its proof, but is not far off. We're going to let b to the log base b of x equal, what we want to show that that's equal to x. We're going to let b to the log base b of x equal to y, convert to exponential form. Remember, in exponential form, so here, I'm converting to logarithmic form. I wrote that incorrectly, sorry. So we're converting, come on, erase, dude. Okay. We're converting to log form. So here, remember, logarithms, we solve for the exponent. So we're going to do log base b, that's the exponent of x, is equal to the base of the exponential is there. Those correspond, and then the y corresponds. That's how I rewrote this, or else it gets like really busy with all the logarithms, right? That implies, based on the proof we did before, if we have log base b on both sides, that the stuff inside the logarithms must equal each other. So x must equal y, and therefore I can substitute in for that y here and prove that the b to the log base b of x is equal to x. So in other words, they kind of cancel each other out. Those are all the properties. Now, or some of the properties, there are a couple others that we will be doing. But if I had something like e to the natural log of 7x, based on that, I know essentially they don't technically cancel each other out, but if you think of that, they undo each other. This is just going to be 7x. Or if I had, for example, log base 7 of 7 to the 4x. Same idea here. It's just going to be 4x.